This is Lecture 5, Foundations of Statistical Inference. By the end of this lecture, you should be able to understand why it is difficult to make inferences from one sample, calculate and interpret a confidence interval around the mean of a sample, and interpret a confidence interval around a sample proportion. In the previous lectures, you learned how to calculate simple statistics in order to describe the characteristics of a variable. Typically, when we calculate statistics for a variable, we do not use data from the entire population of cases. A variable's population is the entire universe of cases that we could potentially collect data on. We do not analyze data for the entire population because it would be impossible to identify every single potential case to collect data on. Instead, we normally work with samples, which are a subset of the population. When we work with samples, we make inferences from our samples and apply them to the entire population of cases. For example, we might collect data on the number of protests and democracies throughout the world in a year, but only examine 20 democracies. We could assume that the average number of protests in a year in those 20 democracies would be close to the average number of protests and democracies per year in the entire world. However, this could be a problem if our sample statistics do not accurately reflect the true population parameters. Here is a real-world example of how applying sample statistics to an entire population could be a problem. Imagine I collected data on the percent of people living below $2 a day in less developed countries. In all, there were 124 LDCs in total. After I collected this data, I found that the population mean, denoted by the Greek symbol mu, for this variable was 34.8. So on average, 34.8 of people living in LDCs live below $2 a day. Now imagine that instead of collecting data on all cases, I took a random sample of 10 countries. For this sample, the sample mean, denoted by x bar, was 29.4. Based on this data, I would conclude that 29.4% of people in LDCs live below $2 a day. Clearly, this value is not truly reflective of the true population mean of 34.8. So our sample estimate has some error in it. In order to illustrate how far off a sample mean can be, I created 10 random samples from the dataset of the 124 LDCs. The averages for the percent living below $2 a day variable range from 19.6 to 46.7. As you can see, different samples can lead you to draw different conclusions about the true population mean. Clearly, these values are often not perfectly reflective of the true population mean of 34.8. So, once again, sample means often do not equal population means. This is a problem since we use sample means to make conclusions about population means. There's also a problem for estimating the standard deviation of a variable. The population standard deviation will always be smaller than the sample standard deviation. To illustrate this point, here are the statistics from the population living under $2 a day example. The population standard deviation, sigma, was 24. I calculated these values on my own. You do not need to know how to do this. The sample standard deviation S was 25.5. Because we know that our sample means will not always perfectly reflect our population mean, instead of just calculating a mean, we could instead calculate a range of potential means. We can do this by calculating a confidence interval around our mean. It tells us the range of potential population means from the lowest to the highest values. But before I teach you how to calculate a confidence interval, I need to discuss how we know we can confidently estimate a range of potential means of a population mean from a sample. We can do this because of something called the central limit theorem. The central limit theorem tells us that if we collect an infinite amount of samples, let's say we take an infinite amount of samples of 1,000 observations each, 95% of the time, the sample means from each of those samples will be very close to the true population mean. This is because the distribution of the sample means is normally distributed. So just for a visual representation, here's a picture of a potential distribution of sample means. Imagine this is the true mean here. 95% of the time, when I take a sample of 1,000 observations, the mean of that sample will be within 2 standard units of this population mean. So, even though our sample mean often will not equal the true population mean, the sample mean will be close to the true population mean. Before I move on, I would like to talk a little bit more about normal distributions. Normal distributions have one mode, so they are unimodal, and they are shaped like a bell. Normal distributions are symmetrical, meaning that if you fold them in half, each half will have the exact same shape. In other words, they have no skew. In addition, the center of a normal distribution is the mean, median, and mode of that distribution. Next, 68% of the values of the normal distribution are within 1 standard unit from the mean. 95% of the values of a normal distribution are within 2 standard units from the mean. And 99% of the values of a normal distribution are within 3 standard units from the mean. Standard units take into account the standard deviation and sample size, which we will talk more about soon. These characteristics mean that 68% of the time a sample mean should be within plus or minus 1 standard unit of the true population mean, and 95% of the time a sample mean should be within plus or minus 2 standard units of the true population mean, and 99.7% of the time a sample mean should be within plus or minus 3 standard units of the true population mean. Using the concepts of the central limit theorem and the normal curve, statisticians developed 2 hypothetical distributions to use in statistical analysis, the z-distribution and the t-distributions. The z-distribution is a hypothetical normal curve that has a mean of 0 and a standard deviation of 1. You could take the values of a variable and mathematically transform them into z-scores. This allows us to analyze variables with small values, such as in tens, and variables with large values, such as in millions, on the same scale. I'm not going to teach you the equations necessary to transform the values of a variable onto the z-distribution. However, I will tell you that whenever you do take a variable's value and transform it into a z-score, the calculation for the mean of the variable will always result in a value of 0. This is because the z-distribution has a mean of 0. In addition, recall that the z-distribution is a normal distribution, so 68% of the values are within 1 standard unit from the mean, 95% of the values are within 2 standard units from the mean, and 99.7% of the values are within 3 standard units from the mean. Although the z-distribution is a useful tool, it does not take into account that some samples are small and some samples are large. With smaller samples, we have less confidence in our data because there's less information. With larger samples, we have more confidence in our data because there's more information. The t-distribution allows us to take into account differences in sample size when analyzing our data. The t-distribution is actually a set of distributions that account for sample size. The smaller the sample size, the larger the variance in a t-distribution. The larger the sample size, the smaller the variance is in a t-distribution. Here is a visual representation of the t-distributions. The z-distribution has the smallest variance, so 95% of the time the observations are very close to the mean. The t-distribution for a sample size of less than 30 has the largest variance, so 95% of the time the observations are quite far from the mean. And the t-distribution for a sample of 30, the variance is moderate here, so 95% of the time the observations are somewhat close to the mean. Now I'm going to show you how to use the t-distribution to estimate a population mean. To do this, we will calculate a 95% confidence interval around a sample mean. The confidence interval allows us to make a low estimate of our mean and a high estimate of our mean. I will use the following data to demonstrate how to calculate a confidence interval for a sample mean. Imagine I collected data on the percent of people living below $2 a day in 10 LDCs. The first step in calculating a confidence interval is to calculate the sample mean of the data. The mean of this data here was 29.4. Next, you calculate the standard error of the sample mean. To do this, you take the sample standard deviation, which I taught you how to calculate in a previous lecture, and divide that value by the square root of the number of observations. The sample standard deviation of this variable was 25.5, and the number of observations was 10. So 25.5 divided by the square root of 10 is 8.1. Next, we have to calculate something called the degrees of freedom. The degrees of freedom is the number of observations in our data set minus 1. So we had 10 observations. 10 minus 1 is 9. We use our degrees of freedom to find the value from the t-table that we will use to calculate the confidence interval. You will use this t-table to find your t-values in this class. On the left-hand column is your degrees of freedom rows. There you will find the row that corresponds to the value of your degrees of freedom. If the value is not listed, choose the closest lowest number. Since our degrees of freedom was 9, we will use the 9 row. After you choose the right row, you must find the right column. The column headings tell you the percentage of cases under the top portion of the t-distribution curve. So for the 0.05 column, it is 0.05 or 5% in the upper part of the curve. Although the table only focuses on the top of the curve, we want to know the area under both ends of the curve because we are calculating a lower bound of a confidence interval and an upper bound. That also means that if we are examining the area under the top and bottom of the curve, we would have 0.05 in the upper half and 0.05 in the lower half. If we add 0.05 and 0.05 together, we have a total of 0.10 under the entire curve. So if we want a 95% confidence interval, we want 0.05 under the curve. To do so, we will want to look at the 0.025 column as it indicates 0.025 in the upper half of the curve and 0.025 in the lower half of the curve, for a total of 0.05 under the curve. So we use the 0.025 column to calculate the confidence interval and the 9 row in our example. So the t-value that corresponds to the 0.025 column in the 9 row is 2.262. Note, from this point forward, you will always be required to use the 0.025 column for confidence intervals, so you should just make a note somewhere to use the 0.025 column for confidence intervals. Now we have all the information we need to calculate our confidence interval. The lower bound of the confidence interval is the sample mean minus the t-value times the standard error. In this case, the calculation would be 29.4 minus 2.262 times 8.1 for a value of 11.1. The upper bound of the confidence interval is the sample mean plus the t-value times the standard error. In this case, the calculation would be 29.4 plus 2.262 times 8.1 for a value of 47.7. Now we are finished calculating the confidence interval, we can interpret it. We would say that we have 95% confidence that the true mean of our variable lies between the lower and upper bound that we calculated. Or, applying it to our example, we would say we have 95% confidence that the true mean of our variable lies between 11.1 and 47.7. We could also say we have 95% confidence that the true mean of our variable is the mean of the variable plus or minus the t-value times the standard error. Or we could say we have 95% confidence that the true mean of our variable is 29.4 plus or minus 18.3.